Hello everybody. Today we will be discussing about a few aspects of Lagrangian mechanics. Okay, so let us start. So what have we discussed so far? We said that we can cast our mechanical problem in the following way. We know the configuration of the system at a time t1 and the configurations, let us call them q1. So q1 is essentially I'm writing it for all the different queues. So I know all the different queues at the time t1. So that's all the different queues are denoted by q1 here. Similarly here t2, and I know all the different queues. So I know the configuration of the system at t equals to t1 and t equals to t2. Absolutely. I am asking the question now that what will be the trajectories of the system, or what will be the set of configurations at all times between t1 and t2, and what the system will eventually follow. Let me denote that by this line. Okay, now I am supposed to figure that out. So what I do, I say that first of all I define a function which I call the Lagrangian function, which is given by all q's. So let me write it as qi, and when I say given by all qi's, it's obviously is a function of time. They are function of time, so that is the trajectory. And it can also depend on time in general. So this is specific to the system. Right? Now what do I do? What I do is the following. I calculate this. Now before I writing that, let me again tell you what this function is. This function has to be, is a function, L is a function of three things. One is of course time, and the others are how does q changes with time and how does q dot changes with time. Which means to calculate this function between t1 and to calculate this function, I need to know a path in this configuration space over which I will calculate my function L. Okay, so this is any path. I can do it for any path. So if I choose q as a function of t, qi, all qi as a function of t, and qi dot, all qi dot as a function of t, then I know what is my L. Okay, and then what I do for that particular path, I calculate, and I'm not always writing the time dependence explicitly. I calculate this, and this I call the action. And we look at now what will this depend on? Depends on the path, right? So let me go back once again and remind you that I have written down the Lagrangian, the functional form of L about qi and qi dot and t depend on which system I am working with. So that is fixed. We'll say choose the system, but that still doesn't choose what is the value of L, because for different trajectories for the given system, L can be different. So I choose a trajectory and then calculate this integral. Okay, and so which means that this S depends on which path I have chosen. So then what do? We look for delta S equals 0. So if I know when is my delta S equals to 0, that will give me the trajectory. And that is essentially my Hamilton's principle. So just like for the D'Alembert's principle, we are exploring all the nearby points where delta W prime was going to be 0. Here we are exploring all the paths. So I cannot only do it for one path and then I will find it. So I have to do it for all the possible paths. And then when I will hit that particular path, which is the actual trajectory. So this is the actual trajectory. What do I mean by the actual trajectory? I mean that if these are the points where the system is at T1 and T2, and if the system is following a particular Lagrangian form, then this is the path that the trajectory will follow that the system will follow between T1 and T2. So that's what I mean by actual trajectory. And when I calculate the action in all the paths, it will change least when I go out of the actual trajectory. So that's why also it is called a least action principle. Now this is not the only least action principle. There are other least action principles also, but mostly we will talk about only this principle. You can learn about the others and we can discuss later. But this is the Hamilton's principle, which is one of the least action principles which we have talked about. And using this, we found that the equations of motions can be written this way. Remember that we also said that we can write down the Lagrangian with any choice of coordinate. The way Hamilton's principle describes it is not required that it has to be in the generalized coordinates, though I have written in terms of q, but it will be true for any type of coordinates. It can be worked out. Okay, so I said the equations of motion, and those equations of motion, which are the Euler-Lagrange equations of motion, that depends on how many coordinates you have used to write down the Lagrangian. So let me be a little bit more specific at this stage, that when I wrote down that the Lagrangian is a function of qi dot and t, if I have n q's, so if I have n q's, so I am working with an n-dimensional coordinate system. I have n of qi's here, n of qi's here, and one time here. So the Lagrangian is actually a function of, can be a function of 2n plus 1 variables. Okay, and out of those I get n equations. So these are the n differential equations. And they are of second order, n second order differential equation. So I will need 2n initial conditions to solve them. Okay, this we have learned last time. So these are called the Euler-Lagrange equations of motion. Right? Now you see, in the case of D'Alembert's principle, we had the delta W equals 0, and we wrote it with a delta because that work done corresponds to a virtual displacement. So here I write delta for what we call the variation of the path. If you think about it a little bit, and if you go through the previous lecture once more after hearing what I'm going to tell you now, you can convince yourself that these variations of different paths actually are the virtual displacements that we were talking about earlier. They are equivalent. The only difference is that here we are looking at the variation over the entire path, and there we were looking at the variation at each instant of the path. Okay, so that's the only difference. Otherwise, they're actually the same thing. Okay, so this is what we learned last time mostly. So let us proceed forward with this amount of knowledge. And let us take a particular case of the Lagrangian. So before we go further, let me put this in bracket because this is something that we may need quite a bit. And let me also keep this in bracket, which is defining the Lagrangian function, which is a function n of nqi. I'm sorry, nqi, nqi dot, and t. And let me also remind you that, not remind you, rather let me also tell you about some convention. It's called the summation convention, and it may be useful for us. So what is the summation convention? It was devised by Einstein because he had to work with a lot of such summations in the general relativity. The summation convention tells you that, say I have to sum over something, and then say I have to sum over two things which are like a and b, and I have to sum over 1 to n. And here what all I am doing is I am multiplying the ith component of A with the ith component of D, and then adding all for all I. So he proposed that this can be equivalently written as, just you don't write the summation, just write this like this. So if an index is repeated, it is summed over. So this is our understanding. So this is our convention. So the summation convention is that if any index is repeated, you just assume that it is already summed over. So you don't need to write the summation symbol here anymore. You don't write it. Okay, so that is Einstein's summation convention, and we may be using it in some of the discussions today. So that's why I wanted to introduce it to you. Okay, special case. Lagrangian does not depend on time explicitly. Which means L just depends on qi dot and no t. So I am writing t and then cross it out. Okay. So we want to look at that special case. Now in general, how do I write? So if I have L, so dl dt, what will be dl dt? Now this is a total derivative, right? So this is total derivative. Which means how does n changes with time? Now that may be just because L is explicitly dependent on time, so I can have a change of L with respect to time like this, and then I should write dt over here, but that is is 1, so that is just 1, and then I will have to write all the other, so del L del qi, then I get dqi dt. But you see that dqi dt is nothing but qi dot, so I can replace that with qi dot. So this is nothing but qi dot. This is nothing but qi dot. So I can just replace it with qi dot. So let me do that. And then I will have the variation with respect to dqi dot, and let me keep this as dqi dot dt. If it is a generalized coordinates, dqi dot dt alone is not the acceleration. Because of that, I did not write it qi double dot. I can write that, but it may give you a wrong impression. So that's why I avoided it. But this is the case. So this is always true. So this equation, this is always true. In fact, this is the definition of del L del T if L is a function of these three variables, right? It doesn't matter which system you are looking at. It even doesn't care about which trajectories you are looking at. Okay. Now, if I am on the trajectory of the particle, so along the trajectory followed by the particle, so how do I get the trajectory followed by the particle? Well, I get it from the Euler-Lagrange equation, right? So the Euler-Lagrange equation must be true for the trajectory followed by the particle. And that depends on now which system you are looking at, etc. I mean, the trajectory depends on which system you are looking at. Well, one thing I have done here, if you have not noticed, that I have not put a summation sign over here because I have both I index in two of these, so that essentially means it is repeated. Otherwise, I should have put a summation sign, but I have already used the Einstein summation convention. I'm sorry, so there is no qi dot over there. So this is equals to 0. So this is Euler-Lagrange equation, and I can also write it, you will not quarrel with me if I write it this way. This is only true along the trajectory of the particle. You will not kill me if I say that I don't know the trajectory at this point, but I know that this will still be true along the trajectory of the particle. Now, if you look at the previous expression, you have del L del Qi, you have del L del Qi over there, so I can just replace this with that. And if I do that, then what do I get? I get dl dt equals del L del T plus, so this is ddt of del L del Qi dot, and then Qi dot, and then the next term is del L del Qi dot and ddt of Qi dot, right? Now you see something interesting has happened. If I look at these two terms, ddt of this keeping that fixed, and then keeping the first term fixed, and ddt of that, which means these two terms I can write together as ddt of del L del Qi dot Qi dot, right? And let me do a little bit of rearrangement here. Let me bring this del L del T in this side, so this becomes minus ddt of L essentially, and let me put this in the left hand side, says that this becomes minus del L del T. And then you can write this as del L del T minus del L del T equals ddt of del L del Qi dot Qi dot. Sorry, so I just want to keep the L also in the same time derivative. Okay, so this is true in general along the trajectory. So this is true in general And this is a remarkable equation. This left hand side you have partial derivative, in the right hand side you have total derivative. Which means the left hand side is the explicit dependence of time on L, right hand side is the total dependence of time with respect to total derivative of time of this entire quantity, right? Now if I have, if Lagrangian is, if L does not depend on time explicitly, if L does not depend on time explicitly, so what is the mathematical statement for that? That is essentially del L del T equals 0, right? Which means that ddt of this entire thing becomes 0, and which means that I can write del L del Qi dot minus L is a constant. It's a constant of time. So let me write the statement here clearly. This is true along the trajectory when Lagrangian doesn't depend on time explicitly, that is del L del T equals 0. C is independent of time. Right? Now this result has a name. It is called this Beltrami identity. Okay. Now we already know, so if I have to define a momentum, see, so far we have not talked about momentum at all. It did not come into our picture. If I am using Newton's laws, the Newton's second law is talking about the rate of change of momentum. Here, so far we have not talked about momentum at all. But if I have to define a momentum, one way is the following. So for each Qi, the corresponding canonical momentum is called Pi, and this is calculated by del L del Qi dot. This is the definition. Okay, so this is the definition. You cannot ask why it is so. This is how a canonical momentum. So this is a canonical momentum, and there can be momentum defined many other ways, but this is the canonical momentum, and it is defined this way. Okay, which means that this previous equation you can write as Pi, and you see that I again have I repeated, which means that it is summed over. So this is equals to constant, and later you will see that this constant in this particular case is nothing but the energy. So this you will see when you learn the Hamiltonian mechanics. Okay, so we understood one thing here now, that if the Lagrangian doesn't depend on time explicitly, then along the trajectory there is something of the system that does not change, and that something of the system is defined in terms of the Lagrangian this way. Okay, so that we have understood. And this is a big result, because if this something does not change along the trajectory, maybe I'll be able to use this something to find the trajectory. Okay, and when you'll go to the example of the central force, we will see how that works out. Okay, so this is so far so good. This is about one property of a particular type of Lagrangian, and I also defined as a pass, I also defined the canonical momentum for you. And we'll come back to the canonical momentum later, but before that, let us look at what we are doing here mathematically. So if you look at carefully, what we have done is equivalent to the following case. So I have a function, say capital F. It is a function of variable y. The y depends on x explicitly. It's also a function of y prime, which is nothing but dy dx, and it can also depend on x. And what all I am doing is I am summing it over, or integrating it over all x between x1 and x2, and defining that with the action. Now, given a function, given how y depends on x, I have a value for s, right? And I can vary now function yx, and as I vary the function yx, I can seek for extrema of x of s, sorry. So this type of problem has a name. It's called the calculus of variation. Okay. And it is not only used in classical mechanics in the form that I have shown you, it is used in many other cases. So let me give you at least a couple of examples. And one example, and I think that I will not work out either of the examples, and that will be your homework to work out the examples completely. And then for the first example, so let me tell you the example and then tell you why I am telling you about it. So this is a completely different problem. The problem is the following. So I have a beach, a sea beach, where a lot of people are playing around, swimming, and there are coast guards in the beach. Okay, so let me draw a sea beach. So this is a line between the sea and the sand part of the beach. So you have water here. So this is the part water. Okay, and in this side is sand. This is sand. Okay. Now there are coast guards, and their job is to ensure the safety of the tourists. And it turns out that there is one tourist here who is drowning, and he is shouting for help. So let me make the tourist colorful. He's drowning and shouting for help. And that was listened by a coast guard who is stationary here. Okay. So what he has to do? He has to go and save the tourist. So that's his job. That's a part of his job. So what will he do? That is the question. Now, In the sand part, if he walks, he will try to walk in straight line. That is obviously, or even if he runs, because then he has a chance to reach that person who is drowning faster, and you want to reach him faster because otherwise there is the best chance that he can save that person, right? Fine. So when he runs in the sand, he has a velocity, say vw, v sand, vs, and let me define this distance as ls. Then similarly, this distance I call, say, L water. And when he runs in the water, well, he doesn't run in the water. That person is drowning, means it's quite deep into the water, must be. So this, he swims in the water, and that speed is V water. Now the question is, what is the path that he will follow? So will he follow this path? Now, see, if we follow this path, okay, so let us start from an extreme path. Say he follow this path. Okay. Now, for this path is very good because he spends most of the time in the sand where the speed is less, and then goes a little bit in the water where the speed is, okay, sorry, the speed in the sand is obviously higher, so he spends most of the time where he can run at the fastest speed, and then he goes to the water, there he spends less amount of time. He must be very clever. But you realize then that he has to spend a lot of time here, so maybe he will try to minimize that by going this way. So he spend equal amount of, according to this figure, equal amount of distance in both sand and water, and then maybe he will be able to maximize this. But somebody may also try to go like this, where which doesn't look very good, because though you spend very less amount of time in the sand, you spend a lot of time in the water, which where your speed is less, so it's not supposed to be good. So the question is that what path he should follow if he knows physics and mathematics, etc. How do I figure it out? To figure it out, so let us see that what we have to do. So that person has to go from one point to the other. Let us name those points. So let me choose the origin here, such that this point now I can label as 0 minus ls. Okay, and this point is then labeled as, so maybe he is at x0 and lw. Okay, so let me call this as point 1 and call this as point 2. So what he has to do is to minimize the time, and the time is given by point 1 to point 2, and if infinitesimal displacement is time step is dt, so this is p1 to p2 dt, right? But that is not written in terms of any of these variables, so how do I write it? Well, you will say that, well, dt I can write as distance, obviously infinitesimal distance, by velocity, and that must be instantaneous velocity, because I am talking about a differential change in time. What is the velocity at that time? That is what will matter, right? Nice. So can we calculate this out? Well, here I can call this, say, x-axis, and that's why I have written x0 over there. So call this, say, y-axis. So if it is so, then I can write the instantaneous distance ds as dx square plus dy square, square root of that, and that I can write, I can take dx outside, and this just becomes 1 plus y prime, the function of x, to the power half dx. Then what I can do is I can break this integral. So I can say, well, I don't know exactly what path he will follow, but I can say that, okay, so he goes up to a point x in sand, and then he goes into the water. So I break this integral into two pieces. One is from P1 to that point. So let's call this intermediate point as P small I. And then, so this is all about water, all about sand. And then Pi to P2. And dt I can now replace as ds. So this is essentially ds and by velocity. So the first will be the velocity in sand, and in the numerator you will have ds, which we have calculated just above. So this is dx, and x goes from 0 to xi. And then I have to add the water part, which will now go from xi to x0, 1 plus y prime x to the power half, but now divided by v water. You see, the velocities were supposed to be instantaneous, but the velocities we have assumed doesn't change while he is in sand or while he is in water. So those are constants which may come out of this integral. But what does the result of this integral depend on? It depends on xi, because everything else is known. Xi is something unknown, so it will depend on xi. And you can see that here the xi decides which path the particle, the coast guard will take, right? If I now look at this integrals, what does the integrals depend on? Integrands. Integrand depend on y prime, right? So in general, if you look at these, this has the form x1 to x2 L y prime x dx. In this particular case, it is only a function of y prime, but it has this form. Okay. So what I ask you to do now, first figure out what you will write for y prime, and then put that over there. See, okay, let me give you a hint what you will write for y prime. See, y prime is the derivative, right? So y prime is essentially dy by dx, which is nothing but the slope of the path at that particular point. So if I am in the water, y prime is the slope of this line essentially, and that is simply this LW divided by x minus x naught. So that's what you have to replace y prime for in the water region, and then similarly you can replace the y prime in the sand region. Once you do that, you can do the integrals now. You get txi, and then you do the variation with respect to xi, and you'll find out for what xi, what is the value of xi for which txi is minimum. That will be the coast guard's trajectory. The coast guard is educated enough, right? Please do that, and once you do that, you may find something which is so interesting, and then you will realize that where this problem comes from. And where this problem comes from, if you realize that, then you will realize that this is a principle of least time instead of action. That is being used in that particular area of physics. Okay, so that is one example we talked about. Let us talk about another example which comes from mechanics. So it's quite from our home right now. This is also an example of principle of least time. So what is the example? The example is the following. So let me again draw the axis such that it becomes easier for us later on. And when I'm drawing this I'm assuming that all the motions are happening in 2 dimension. You can do it in 3 dimension also, but 2 dimension suffices for this motion. Why, that we'll learn again in a week from now. So that's the origin of my coordinate system. Now I call this y, we call this x. This is obviously the negative y-axis. That y only means that it's the y-axis. And then I have gravity, which pulls downwards. So there is a gravitational force downwards. Okay. What you have to do, a particle is in this position initially, and the particle will eventually come here. It has to come here, P2, which I can denote as x naught minus y naught, minus because it's below P1. It has to come this way under the influence of gravity. So the question is, so the particle has to come, the particle has to come to P2 from P1 in least amount of time. You see, it's a principle of least time. So this has a name. The name is called Brachistochrone problem. Chrone means time, and I cannot break out the rest of it for you because I don't know how this German name works, but it's essentially telling you what is the path for the shortest time. So it can be like this, it can be like this straight line, if you think it can be like that, it can even be like this. So which one? That is a question. And if you start thinking about it, you will again have the same dilemma, because you may think that it follows a straight line, but then you will realize that it is not using up the gravitational force. So it may be that it is easy to come here by using the gravitational force and then go this way. So there can be many such possibilities which you can think of. But how do I solve this problem? Using the calculus of variation. But how do I solve this problem? Using the calculus of variation that we have just learned. So again, this is a problem of principle of least time. So I start by defining the time equals, and this, then I have to go from P1 to P2 and then dt. And this we had actually worked out already. So this is P1 to P2, infinitesimal distance. This is just from the previous problem or example, by instantaneous velocity. And now, what is the infinitesimal distance? Well, that we worked out here. It comes out to be this, ds equals that. So I just write that down. I'm sorry. So this, there is a dy squared there, so all these will come with a square, which I forgot. I just realized now. Okay, now what do I do? Well, I can now say that, well, in this problem, if I look at this point, what is the value of the value of this C which we discussed here, this C. Okay. What is C? Well, as we know already, as I told you as a past time, that this C is nothing but the energy. C is the energy. Then I can write that as half mv squared minus gy, and this is the constant energy, right? Now you see, gy is the potential energy. I can choose it in such a way that the potential energy, I can choose the potential energy in such a way. See, I am free to choose the zero of the potential energy in kinetic, in the in classical mechanics. I can choose whatever I call zero of the potential energy. That is, I have free choice. I don't have that free choice in the quantum mechanics, as you know that there are 0 points energies in quantum mechanics. But classical mechanics, I can always choose zero of the potential energy. So I choose the potential energy such that at P1, that C is equals to 0. And if it is so, then I get half mv squared is g times y. And that gives me v, this is a constant, and then I have root over of y. Okay, so let us calculate the time taken, which is an integral from x1 to x1 is 0, so integral from 0 to x0. So this point is P1 is at 0 and P2 it is x0. And then I have in the numerator 1 plus y prime square to the power half. In the denominator I have v, and the v I can take this constant terms outside, m by 2g, and what remains is root over of y, and I have to integrate over x. Right? And you see again, I have come up with a case. I can just compare this with x1 to x2. This is a variational problem, y prime x dx. And you directly read off the Lagrangian, which is a function of y prime and x, in this case is nothing but root over of m by 2g 1 plus y prime square to the power half by root y. Right? So this is the Lagrangian, and if you have not noticed already, it is independent of x. Okay, that actually we have already used. Well, you have not used that. Okay, so I have not used that. We have used the fact that the system is conservative force gravity. Because of that, this comes about. Now we are saying that Lagrangian is independent of x. There is no explicit dependent of x in this, which means now I can use Bernoulli identity, or I can just write down the Euler-Lagrange equation for this. What will be the Euler-Lagrange equation for this, by the way? So it will be d dx of del L del y prime minus del L del y equals 0. And that is essentially, if I solve this equation, I will get y as a function of x. So this will give me y as a function of x. And that's what we wanted. What is y as a function of x? That is the curve. That is this curve. This curve is y as a function of x. Okay. So I will not solve it for you. It will take quite some time to solve it here. in a discussion. So I'll leave it for you to solve that. So that is your second homework today. All right, that's it for today. Thank you.